Over the years, MasterTech has brought you the latest information about automotive service and diagnosis in an effort to make your job easier. The area of powertrain diagnosis can be particularly complicated, especially if you don't have the information and resources needed to get the job done. And when troubleshooting powertrains, it's especially important to understand how onboard diagnostics works. Because onboard diagnostics can be so complex, we've featured it a number of times in the past. MasterTech first introduced you to the second generation of onboard diagnostics, or OBD2, in January of 1994, when it was initially used on the Neon. We followed that up in November of 1995 by providing you with the latest changes that had occurred to OBD2. This included the use of freeze-frame data and the similar conditions window. As the OBD2 phase-in process continued, 1 year later, we again gave you an update which included some current service concerns. And in 1998, we devoted a program to one specific aspect of OBD2, the misfire monitor. Now it's 2001, and as you know, all Chrysler, Dodge, and Jeep vehicles are equipped with OBD2. For this reason, we thought this would be a good time to not only refresh your memory, but also tell you about the newest changes occurring in OBD2 technology. This month, we'll begin by looking at an overview of onboard diagnostics. After that, we'll see how onboard diagnostics works. And finally, we'll go over some diagnostic tips that you'll be able to use when working with onboard diagnostics. While vehicles today require more sophisticated technology than ever, it's important you remember that generally much of what happens in their engines and related systems predates electronic control technology. If you come across a vehicle with drivability issues and no fault codes present, diagnosis may be no different than it has been in the past. For example, if you have a vehicle that is sluggish, the reason could be low fuel pressure caused by such things as a clogged fuel filter or a faulty pump or fuel pressure regulator. If the engine seems to be losing power, you may want to check cylinder compression or check for a plugged catalytic converter or even a collapsed exhaust pipe. Remember that something as simple as an exhaust leak can mislead the PCM when the oxygen sensors report the additional air in the exhaust. Whatever the cause, just remember sometimes vehicle diagnosis requires an understanding of the fundamentals of engine operation. With that said, before we look at the changes that have occurred in the area of onboard diagnostics, let's take a minute to go over the reasons that it's used today. Over the years, the federal government has passed legislation in order to help maintain air quality standards. Onboard diagnostics is the result of a mandate by the California Air Resources Board, or CARB, and federal EPA. In the second generation of onboard diagnostics, CARB requires that systems not only warn the driver of component failure, but also monitor both systems and components for conditions that would lead to a specified increase in emissions. For this reason, all automotive manufacturers were to develop a system that monitored the performance of emission systems. The intent is to alert the driver in the event of system or component failure that would cause an increase in tailpipe emissions above a predetermined threshold. Each manufacturer was free to develop its own system of monitoring. However, the result had to be the same: early detection and warning of conditions that could cause vehicle emissions to exceed the standard. This provides a consistency of system testing between manufacturers and, in effect, contributes to cleaner running vehicles. The methods Daimler-Chrysler uses to implement onboard diagnostics may vary from vehicle to vehicle or from model year to model year. In addition, how OBD works actually depends on the market for which the vehicle is intended. For instance, vehicles meant for the United States monitor the evaporative system for leaks. In some markets, however, evap leak detection is not performed at all. Also, some of the terms used in onboard diagnostics will differ from one market to the next. For example, in the United States, the second generation of onboard diagnostics is referred to as OBD2. However, in Europe, it's called EOBD. While you're not likely to come across these differences during your diagnosis, it's a good idea to be familiar with the various systems and terms. Now let's take a closer look at the way onboard diagnostics works and the hardware changes that were necessary to accommodate it. Once you know how to access and interpret OBD2 data, it makes your job easier because it provides detailed information about engine and emission systems. In onboard diagnostics, the PCM runs a series of diagnostic monitors to test, detect, and identify emission-related faults in the vehicle. You should know that these monitors detect faults by inference and not directly. If the PCM decides that trouble in a monitored circuit would result in a certain increase in emissions, a diagnostic trouble code, or DTC, is stored in the PCM's memory, and the driver is notified of a concern by the illumination of the malfunction indicator lamp, or MIL, which can be seen as either a check engine lamp, service engine soon lamp, or the ISO engine symbol. Sometimes the PCM illuminates the MIL when it detects the fault the first time, but usually it takes 2 consecutive occurrences for the fault to mature. In other words, for the PCM to decide that an emissions-related condition does in fact exist. When a vehicle comes to your dealership with the MIL illuminated, you can read the fault description by using the DRB3. And for 2001, PCM trouble codes can be displayed in the odometer on all vehicles, regardless of whether or not they use the PCI bus. By cycling the ignition key on, off, on, existing trouble codes will be displayed. When the PCM detects faults, it also stores freeze frame data in its memory. Storage of this freeze frame 1 data is also mandated by CARB. Like DTCs, this information can also be viewed with the DRB3. Starting with the 2000 PCM software, significant enhancements have been made with the addition of a second freeze frame that will generally store the most recent fault and up to 27 items. Also, newer PCMs, like the Next Generation Controller and Siemens Controller, will now allow up to 5 freeze frames to be stored. You'll learn more about the Next Generation Controller, or NGC, in an upcoming MasterTech program. At this point, we need to look at the MIL in more detail, since the way it illuminates is tied into OBD operation. A solid MIL at key on indicates that the system is performing a bulb check. If the bulb does not illuminate, you'll need to troubleshoot the bulb or bulb circuit. A solid MIL while the engine is running means that a fault has been detected and is present. A flashing MIL at key on with the engine off and after the bulb check is complete indicates that customer readiness indicators have not been completed. This means that all of the monitors have not been run and that in some areas emissions testing cannot be performed yet. This MIL strategy is used on most 2001 S-Spec vehicles and is new for JTEC in the 2002 model year. Finally, a flashing MIL while the engine is running indicates catalyst damaging misfire, which must be corrected before further damage results. Malfunction indicator lamp operation is just one of a few physical changes that were necessary to accommodate onboard diagnostics. For example, each system now utilizes an upstream and a downstream oxygen sensor. The upstream O2 sensor, located between the engine and the catalytic converter, was already used for closed-loop system operation. An O2 sensor was added downstream to monitor catalyst efficiency and to help trim the upstream oxygen sensor goal voltage. A standardized connector has been added as a communication link between the DRB3 and various vehicle systems. This data link connector, or DLC, can be found in the same general location on all OBD2 compliant vehicles. OBD has also resulted in strict monitoring of evaporative emissions. One method of attaining this required the addition of a leak detection pump that is used to pressurize the system and check for leaks. We'll be taking a closer look at evaporative leak detection a little later in the program. Now let's look at some of the software changes that have occurred with the addition of onboard diagnostics, starting with testing strategy. As I mentioned earlier, some faults will immediately turn on the MIL, while others will not mature until the second consecutive occurrence. These result in one-trip and two-trip DTCs. In a one-trip DTC, once the PCM detects a fault, it will store a DTC, record a freeze frame, and immediately illuminate the mill. If the fault does not reoccur, after 3 consecutive good trips, the PCM will self-extinguish the mill immediately, or upon cycling the key. In general, a good trip is considered complete after the engine is started and failed monitors have been rerun. If there have been no failed monitors, the trip is complete after the O2 sensor monitor and catalyst monitor have been run. After the mill goes out, the DTC and freeze frame data will remain in memory until 40 warm-up cycles have occurred with no recurrence of the fault. After 40 warm-up cycles, they will be self-erased. A warm-up cycle occurs after an engine shutdown period when the engine coolant temperature has fallen below 160 degrees Fahrenheit. In order for a warm-up cycle to be complete, during vehicle operation, the engine coolant temperature must rise at least 40 degrees Fahrenheit, and the coolant temperature must reach at least 160 degrees Fahrenheit without any further faults. For example, suppose the vehicle's engine coolant temperature is 159 degrees Fahrenheit at startup. The warm-up cycle will complete when temperatures reach 199 degrees Fahrenheit without any further faults. In a two-trip DTC, the first time the PCM detects a fault, a one-trip failure is stored and a freeze frame is recorded. This is called a pending fault. With a two-trip DTC, however, the PCM has been programmed not to store the trouble code or illuminate the mill until there have been 2 consecutive occurrences of a fault. This is called a fault which has matured. During the next trip, when the operating conditions and monitoring conditions have been satisfied, if the fault is again detected, a DTC is set, the freeze frame priority is updated, and the mill is illuminated. If, however, there is no second consecutive occurrence of the fault, the one-trip failure and freeze frame are erased from memory after a good trip has occurred. A final testing strategy is the exponentially weighted moving average, or EWMA monitor, which performs the same test a number of times within the same trip. The EWMA type of monitor will be covered in further detail a little later in the program. Now let's look at another software change that directly affects monitor operation. Software in the PCM, referred to as the task manager, is used to organize and prioritize the diagnostic procedures and the protocol for recording and displaying the results. It also determines whether enabling conditions have been met in order for each monitor to run. In a sense, it's the traffic cop of the onboard diagnostic system. Some conditions may prevent a monitor from running in order to avoid a false failure. These are referred to as pending, conflicting, or suspending conditions. If the mill is illuminated and a DTC is stored in memory, the task manager may not run some monitors until the condition causing the mill and DTC is resolved. This is known as a pending condition. In a conflicting condition, if the PCM is already running a monitor, the task manager may not allow another monitor to run if it will corrupt or conflict with the results of the first monitor and cause a false failure. In a suspending condition, the task manager may postpone maturing a two-trip fault if an existing DTC can affect the results of that monitor. And finally, various factors may inhibit monitor operation altogether. Some monitors will be disabled if ambient temperature, altitude, fuel level, and battery voltage are not in suitable range. Well, this is just the beginning of onboard diagnostics, but by now you can see what a complicated system it can be and why it's so important to understand it fully before you even begin to try to use it during diagnosis. Now let's take a more detailed look at how the onboard diagnostic system operates. Now that you have a better idea of why onboard diagnostics is used and what it does, let's go over some of the specifics of system operation.
As I mentioned earlier, in onboard diagnostics, the task manager runs a series of diagnostic monitors to test, detect, and identify emission-related faults in the vehicle.
All of the monitor tests vary in length and are run by the PCM as soon as enabling conditions have been met. Some of the monitors will be performed only once per trip, while others will run continuously throughout the trip. Once per trip monitors run when enabling conditions are met and may conclude at any time. Once the monitor concludes, it will stop and the results are recorded in memory. At the first detection of a fault, a DTC is stored in memory and a freeze frame is recorded. However, the mill will not be illuminated until the second consecutive occurrence of the fault. In other words, the same fault must occur in the next trip before the mill will be illuminated. This enables the system to verify that a fault really does exist before warning the driver. Once per trip monitors include an O2 sensor monitor, O2 sensor heater monitor, exhaust gas recirculation or EGR monitor, a monitor for the secondary air supply if the vehicle is so equipped, a thermostat monitor, and an evaporative emissions monitor. The O2 sensors provide information about exhaust stream oxygen content to the PCM. When the monitor is conducted by the PCM, the O2 sensors are tested for big slope counts and half-cycle counts. For big slopes, the PCM checks the change in voltage level over time of the O2 sensor. If the slope is great enough, the counter is increased by 1. If the count reaches a predetermined value, the monitor passes. On a faulty O2 sensor, the big slope counter would have a pattern like this. The PCM also monitors the number of times the O2 sensor signal goes beyond the switching points it establishes for the purpose of the monitor. Each time the voltage passes the high and low thresholds, the counter is increased by 1. If the PCM counts a sufficient number of half cycles within a defined time frame, the monitor passes. On a faulty O2 sensor, the half-cycle counter would have a pattern like this. Only one of these tests have to pass in order for the monitor to pass. The conditions for the O2 sensor heater monitor to run will depend on the PCM that the vehicle uses. On vehicles equipped with the S-BEC, the test is run after the vehicle has been driven and then shut off. After the O2 sensors have cooled down, the PCM turns the heaters back on and looks for a change in diagnostic voltage, which indicates that the heaters are functioning properly. However, on vehicles equipped with a JTEC, the test is performed on a cold start. At this time, the monitor looks for a change in diagnostic voltage to be below a certain threshold within a predetermined period of time. The next once-per-trip monitor checks EGR operation. When EGR is flowing, it displaces air in the combustion chamber, which lowers temperatures, thus reducing oxides of nitrogen. When the system is tested, the PCM turns off the EGR solenoid, which causes an increase of oxygen into the combustion chamber. The PCM then compensates by adding fuel. At this time, the EGR monitor looks for the increase of fuel to be above or below a certain level. The 2000 model year marked the beginning of the phase-in process for the thermostat monitor in states requiring California emissions. It's used to monitor the cooling system for proper operation in order to assure the correct temperature has been reached to enable other diagnostics. The evaporative system uses an evaporative emissions monitor, which, in accordance with CARB regulations, checks the EVAP system not only for leaks, but for flow as well. Chrysler, Dodge, and Jeep vehicles use a leak detection pump that you may already be familiar with. However, a new system of natural vacuum leak detection is being phased in on vehicles having the next generation controller. The leak detection pump, or LDP, is run at a cold start. When the enabling conditions are met, the LDP will pressurize the system and check for leaks. You can learn more about leak detection pump operation by watching the July 1996 MasterTech program or the January 2000 MasterTech bonus program. Beginning in the 2002 model year, Another form of leak detection is going to be phased in. All vehicles having the next generation controller will use a system of natural vacuum leak detection, or NVLD. Unlike LDP, on vehicles with NVLD, the EVAP monitor is run during system cooldown. Essentially, what this does is create vacuum as the evaporative system cools. If no vacuum occurs over a period of time, the PCM determines that a leak exists. The Evaporative Emissions Leak Detector, or EELD, Miller Special Tool number 8404, is used to check either system for leaks during diagnosis. This new tool for leak detection replaces the ultrasonic leak detector used previously.
It allows the user to pressurize the evaporative system with shop air and uses a smoke generator to test for small leaks. The smoke generator uses UV dye that will leave signs of a leak under black light.
For more information about how to use the EELD, refer to the January 2001 MasterTech program. Leak detection is just one aspect of the evaporative emissions monitor. The system also uses a separate monitor to test purge flow. It does this in two stages. In stage 1, the PCM compares short-term fuel trim of purge cells to purge-free cells. If there's a significant difference between cells, the PCM assumes that purge is operating and the monitor passes. However, if the difference is not significant, the monitor will move on to stage 2. In stage 2, on vehicles with an LDP, the PCM ramps open the purge solenoid and again looks for a shift in short-term fuel trim. However, on vehicles where an LDP is not used, the PCM will still ramp open the purge solenoid, but in this case, it will look for either a shift in short-term fuel trim, an increase in RPM, or a decrease in idle air control. Well, that just about covers the once-per-trip monitors used on Chrysler, Dodge, and Jeep vehicles. Now let's take a look at the monitors that will run continually throughout the trip.
As I mentioned earlier, when conditions are right, the task manager runs some monitors continuously, unless the monitor fails.
Continuous running monitors are the fuel system monitor, misfire monitor, and comprehensive components monitor. The fuel system monitor checks the fuel control system for a fuel mixture that cannot be corrected without excessive emissions. Here's how it works. The PCM uses short and long-term adaptive memories to determine whether the fuel system is attempting to correct for excessively rich or lean conditions. The monitor uses a slightly different method of determining excessively rich or lean conditions. But both involve multiplying the short-term adaptive memory by the long. If on the basis of this calculation, the PCM determines total fuel correction to result in 1.5 times or more of the FTP emission certification standard, a one-trip failure will be stored in memory. Remember that the fuel system monitor requires 2 trips to fail. So a DTC will not be set, nor the mill illuminated, unless the same failure is detected during the next trip. The next continuous running monitor that we're going to talk about is the misfire monitor, which works by looking for indirect evidence of engine misfire in specific RPM blocks. Using the crankshaft position sensor, the PCM looks for a variation in crankshaft speed, which could indicate misfire. However, before the misfire monitor can become active, the PCM must first learn the adaptive numerator, which establishes a baseline for the particular vehicle. This is necessary due to the mechanical and electrical tolerances in crankshaft position sensing. In order for the PCM to learn the adaptive numerator, it needs to look at crankshaft positioning sensing when it is not affected by combustion. To do this, it monitors the sensor when the vehicle is driven at about 60 miles per hour, followed by a full closed throttle deceleration. Also, the adaptive numerator is cleared from PCM memory anytime the PCM is reflashed or replaced, and anytime the battery is disconnected. Once active, the misfire monitor checks for 2 different types of misfire, Type A and Type B. These are also referred to as catalyst damage and FTP misfire. On all OBD2 vehicles, when catalyst damage misfire occurs, the mill will flash as a warning to the driver to take the vehicle in for service immediately in order to prevent catalyst damage. On S-Spec vehicles built before 1998 and J-Tech vehicles built before 1999, the mill will also flash and a one-trip DTC will be set immediately. However, on these vehicles from this point on, misfire faults became a two-trip fault. In catalyst damage misfire, the PCM will allow a certain misfire count and up to 600 revolutions of the engine before declaring a one-trip fault, unless misfire rate in the first 200 revolutions should exceed a certain threshold. In FTP misfire, also known as Type B misfire, the level of emissions is projected to increase 1.5 times the FTP limit. It allows a certain misfire count in up to 4,000 revolutions before declaring a one-trip failure of a two-trip fault, unless the misfire rate in the first 1,000 revolutions exceeds a certain threshold. If you'd like more information about the misfire monitor, you can refer to the May 1998 MasterTech program. Along with the major monitors, onboard diagnostics also monitors all other components that could affect emissions levels. This is referred to as the Comprehensive Components Monitor. It tests the performance of emission-related electrical components for opens and shorts and features additional checks of components for rationality and functionality. In other words, the PCM checks input signals to verify they make sense when compared to other input signals. And it checks output signals to be sure they have the anticipated effect. Finally, beginning in the 2002 model year, a positive crankcase ventilation, or PCV system monitor, will begin its phase-in plan in states requiring California emissions. It will be used to monitor the integrity of the crankcase ventilation system. In November of 1996, we first introduced you to the exponentially weighted moving average, or EWMA catalyst monitor. If you'll recall, the EWMA catalyst monitor differs from earlier catalyst monitoring technology in that it requires that 6 separate test sequences be run before a failure is recorded. The manner in which the tests are run differ between vehicles having an S-Spec and those with a J-Tech. On S-Spec vehicles, all 6 tests are conducted within the same trip. On J-Tech vehicles, however, the PCM will run 3 tests, then suspend testing for the remainder of the trip after 3 failures are detected. During the next trip, once enabling conditions are met, the PCM will resume testing. If 3 additional failures are detected, the PCM will store a DTC and illuminate the mill. Another important difference between the EWMA catalyst monitor and the early generation catalyst monitor is that the PCM is able to compare the current upstream to downstream O2 sensor switching frequency against stored data from past trips. This allows the PCM to determine if the catalyst is naturally aging or if there's been a catastrophic failure, possibly due to poisoning or misfire. Each time the PCM determines that the instantaneous switching frequency has exceeded the historical data, it will increment the suspicious counter. When the PCM has accumulated 6 suspicious counts, a malfunction is declared. Like the EWMA catalyst monitor, some late model S-Spec vehicles have an EWMA EGR monitor, which is very similar in operation. One last aspect of onboard diagnostics that you may already be familiar with is the similar conditions window. This is a set of parameters for vehicle conditions that must be met for the monitor to retest after the first fault. The similar conditions window only applies to fuel system and misfire monitors. For more information about the similar conditions window, refer to the November 1995 MasterTech program. You can also refer to applicable training course information. That just about covers operation of the onboard diagnostic system. Understanding how it works will prove to be useful when you need to diagnose a system with it. And speaking of which, next we're going to go over to the shop to look at some information that will also prove to be helpful to you during diagnosis. Now that you have a better understanding of onboard diagnostics and how it works, let's take a look at some service concerns that you may come across during your diagnosis. We'll begin by going over a couple of diagnostic capabilities the generic scan tool has that you may not be aware of. First, like the DRB3 in standalone mode, you can use the generic scan tool mode to retrieve fault information. If you'll recall from the December 2000 program, this can be very useful if you were to get a no response message from the PCM while using the DRB3. In order to use the generic scan tool, you need to make sure that your SuperCard 2 is installed in the DRB3. Then, at the DRB3 main menu, select option 3 to put the DRB3 in generic scan tool mode. From the generic scan tool menu, select option number 3, emission-related DTCs. At this time, any existing emissions DTCs will be displayed. The generic scan tool can also be used to seal the evaporative system, so leak detection tools, such as the EELD, can be used to look for leaks. It does this by closing the vent on the leak detection pump and blocking the canister purge solenoid. While the engine is running, from the generic scan tool menu, select option 8, Onboard System Test. Once the selection has been made, the system will seal so leak detection can be performed. For more detailed information about generic scan tool operation, refer to the reference information included with TSB number 1801201. Anytime you test the evaporative system for leaks, however, remember that it's temperature dependent and should only be tested when the system is cold. As fuel in the tank warms, it expands and can mask the leak. A good example of this is an experiment that I used to perform in class to illustrate the effects of heat expansion. When you place an air-filled balloon into a freezer, as it gets cold, it shrinks or contracts. However, when you remove the balloon and the warm air gets to it, it begins to expand. So when temperatures get too high, you may not be able to find a small leak because fuel tank vapor expansion can disguise it. Next, we're going to take a look at this Intrepid that Dan's been diagnosing.
Right. I think there may be a leak in the evaporative system, but I'm having trouble finding it.
Okay, well, start at the beginning and tell us what you've done so far.
Okay. As instructed by the 6-step troubleshooting procedure, I began my diagnosis by verifying the complaint, which was easy enough because the mill was illuminated in the instrument cluster. Next, I tried to determine if there were any related symptoms. I then used the DRB3 to check for DTCs and discovered that there was a leak in the evaporative system. During my visual inspection, I noticed that the gas cap was loose. I then used the evaporative emissions leak detector to look for the leak. However, nothing showed up. Now I'm wondering if it could have been the loose gas cap.
Well, you're off to the right start. Anytime you suspect there's a leak in the evap system, you should always perform a thorough visual inspection before replacing or even disconnecting any components, just as you did. Sometimes disconnecting connections can actually mask a leak condition. Also, on vehicles having a leak detection pump, like this one, in some instances you can get a leak fault when there's really nothing wrong with the system. For this reason, there's a couple of items that you need to be aware of during diagnosis.
Like what?
First, beyond just checking for tightness, you want to make sure the gas cap is in good condition. A loose gas cap could cause a small leak to be detected, but so could a defective one. Before replacing any components, you want to check connections to make sure they're properly seated. And if the trouble code indicated a pinched hose, like P code 1486, you'd want to inspect the evap system hoses and tubes for pinches or blockages. If you still can't find the cause after checking the gas cap, hoses, and connections, you should then refer to the diagnostic procedures for further assistance. I think in this case the cause may have been the loose gas cap that you tightened. But the PCM has not run 3 good trips on the evap system yet. So using the DRB3, let's observe the monitor to see if it passes. To do this, we'll have to start the engine. After the monitor concludes, we see that it didn't fail the 1 trip, and a DTC was not set. For this reason, we know that a leak no longer exists. So the cause of the fault was probably the loose gas cap.
Who'd have thought it could be as simple as that?
You know, not all causes are that simple. In fact, some faults that you get can be quite misleading.
Yeah, like that other Intrepid I had in here the other day. A check for DTCs brought up fault P1494, which is leak detection pump switch or mechanical fault. I assumed that the leak detection pump was faulty, but I wanted to be sure before I replaced it. So I followed the steps in the diagnostic procedures to narrow down the cause. I first checked system vacuum using a vacuum gauge at the LDP vacuum supply line. According to the gauge, vacuum supply to the LDP was sufficient. Next, using the DRB3, I attempted to read the LDP switch state. The procedure instructed me to connect a jumper wire between the LDP switch sense circuit and a 12-volt source. However, when I did this, there was no change in the switch state. At this point, I suspected the leak detection pump was good and that the cause had to be somewhere in the switch sense circuit. So I measured the resistance of the LDP switch sense circuit in the LDP harness connector to ground. Resistance of above 5 ohms told me that the circuit was not shorted to ground. I then measured resistance of the LDP switch sense circuit between the LDP harness connector and the PCM harness connector. Resistance should have been below 5 ohms. However, it wasn't. So I knew that I would need to check the LDP switch sense circuit for an open. By following the LDP wiring schematic in the service procedures, I was able to find the source of the fault, which turned out to be a corroded connector. If I had just replaced the leak detection pump without further diagnosis, I would have made the wrong repair.
That's right. And in fact, that fault code is the subject of a TSB. You can refer to TSB number 1800901 for more information about the leak detection pump. This informational TSB also includes a leak detection pump operation and diagnosis booklet, publication number 81-170-00006. One last item that I want to address today concerns vehicle misfire. When diagnosing a misfire, remember that there are factors that can cause a misfire fault other than improper combustion. As you know, the PCM detects misfire by monitoring speed fluctuations at the crankshaft. Anything that could result in speed fluctuations could cause a misfire fault detection. So, when you get a misfire fault during your diagnosis, some of the things to look for include a loose or defective accessory drive belt, a worn belt tensioner, out of round or incorrect installation of the accessory drive pulley, and wiring concerns involving the crankshaft position sensor. Also, look for defects in the engine flywheel or flex plate, or binding of accessories driven by the engine, like the power steering pump, AC compressor, and so on. Finally, on vehicles with a manual transaxle, bucking caused by an inexperienced driver could be misleading to the PCM. By using the DRB3 to observe cylinder action, you can verify whether or not an actual misfire condition exists. A random misfire, like this, indicates that it probably isn't really a misfire and will need to be investigated further. When you see a reading like this, however, because it's consistent on one cylinder, you can be pretty certain that a misfire is present. Well, that concludes this month's Master Tech. Onboard diagnostics can be complicated. However, having the right training and the right resources can make your job of working with it a lot easier.
And watch for us again next month when we'll be discussing 3.7 and 4.7 liter engines.